we're going to start. I guess everybody knows who I am, so I don't need to introduce myself. Kurt really embarrassed me just now, so I'm going to embarrass him back. Remember when Kurt told you about when he met Rolf Richter? Well, when I met Kurt, told me it was the same thing. It was like, this is the guru, I'm meeting the guru. So it was a very pleasant experience for me.
That's the part nobody's going to believe.
Who's going to believe that?
Well, they'll believe that you got to meet the guru, I'll admit that, but that it was a pleasant experience, that's never the case.
No, that's actually, I was like, oh, I get to meet Kurt Tony, I was so excited.
I have a story for you that's a little different. So.
Might not look like that. Okay, I think in the outline we actually said that we're going to tell you a bit of an overview of the different imaging spectroscopy sensors that are right now in orbit and that are in future. The whole reason why we actually decided to embark on this calibration and validation exercise and also the result of why you're getting this course is because we're actually preparing for the next generation of spaceborne imaging or hyperspectral sensors. So this is why we're doing the course, and so this is why I'm actually being asked to actually put up, what are the sensors that we are actually having up there, what do we expect in the future, and what can we do to actually make sure that we can use these sensors in a coherent fashion. So there are labelings there and that we've used. So the green means what current sensors are up there. The yellow orange is terminated missions, and future missions are in blue. So this actually, I have to acknowledge, this was put together by Andreas Müller and Ute Heiden at the DLR of the German Aerospace. I actually stole this from them. So you'll see that we have right now in space, in orbit, the Hyperion, which has been there since the year 2000. And then we have other sensors ranging from the Chinese sensors, which I'm sure you all know about, the HJ1 sensor, and the Russian sensors, such as the RISA sensors, which really, realistically, I personally don't really know too much about. And of course, then we had other sensors that were launched into the International Space Mission, such as the HIPO sensors, which was operating for a while, but now has actually ceased operation. In terms of spatial resolution, you will see that most of the sensors actually operate predominantly in the visible near-infrared and not in the shortwave infrared. So right now, the operational or science satellite that is the only one that's still working up there is the Hyperion sensor. So 16 years on, it's the only one that's been that's been still in orbit, and we really need a visible shortwave infrared sensor up there. So we're really gunning for the next sensor to be launched, of course. In terms of the spatial resolution, you see that they range from roughly 30 meters to really, really good big footprints of 500 meters. So future, this is hope. This is hopefully where we're going in the future. So we have a range of sensors that are going to be operating in the next 5 years that are going to be launched. I'm sorry I lose my voice throughout because I'm feeling like I'm going to lose my voice right now because I'm at the tail end of a cold. So please forgive me, and just if you can't hear me properly, just put up your hand. So we have at least 2 sensors that are going to be launched in the next 2 to 3 years, right? And this is the German NMAP sensor and the Japanese Hisui sensor, which is going to be on the International Space Station. So we can look forward to that. And there are a range of other sensors which are going to be operating in the next 5 years, which to me as an imaging spectroscopy sensor and I would admit I'm fully in love with imaging spectroscopy sensor. That is really an exciting opportunity for our community. And for you guys in China, I see that there is and correct me if I'm wrong, Gaofeng 5 sensor, which will be launched actually towards the end of the year. So you guys are really in a privileged position. So in terms of, if you have a look at the spectral resolution, we go from the visible to the shortwave infrared. So we get that important part of the spectrum that has been missing in all senses, from multispectral to hyperspectral, finally. So this, for me, is a very exciting opportunity. Not because I'm an Ike, Kirk, but because there are so many important features in that part of the wavelength range that can help us understand so much better about what our Earth is like. So in terms of pixel resolution, it actually there's a range, but predominantly in the next 5 years we're going to get 30-meter sensors. So it is that range, but there are also very, very interesting sensors that are actually lower spatial resolution, and also there are bigger footprint ones, of course.
Excuse me.
Yes.
Maybe in this slide, but yes, P3 is on board in ISS. So
yeah, I did say that. I did say that.
Not L3.
Yeah, I did.
So
I did say that in the beginning, right? The history is going to be on the International Space Station.
So now, before in this station, in this situation, our platform will be on the L3, but this project is postponed to the. So we decided to mount it on the ISS. So not L3.
Sorry, I didn't correct this one. I corrected the other one. I'm sorry. I'll correct it before. So I did explain why we want to do this work in Jesus. So that's okay. But the thing is, if you have a look at all the sensors that we have on that are projected for the next 5 years, we'll see that they are either space mission, or there are missions that will not be global or temporal coverage. So how do we get this? Because in the end, we don't want just one-off measurement. If you want to actually understand the trends, I mean, it'd be okay if we are geologists and we go, okay, we map the Earth, we know what is going on. But still, we want wall-to-wall coverage, right? We want to see what's going on throughout the world. And the only way that we think we can do it is if the different spaceborne providers actually work together and make a virtual constellation of sensors. So if we can actually make all these sensors, get the data from all these sensors, then we actually can have potentially wall-to-wall coverage as well as multi-temporal data. And the key to actually getting all these different sensors to actually work together and to be coherently making the same image is calibration or cross-calibration. So, this is, I stole this from Andreas Müller and Infinity Work. This is the virtual constellation of sensors. It doesn't work, I'm sorry.
It will say the peak time is not available.
Oh. I'm sorry. Okay. I'll just play this one, which hopefully works. Is it gonna work? No. I'm sorry. But this, okay. I've lost you. I'm sorry about that. This was actually meant to show you that an example that Kirk had actually provided for me from NASA, where they have 12 sensors all making global precipitation measurement. 12 different sensors get together to make these measurements that are coherent, that actually make sense across all sensors. That's the kind of thing that would be great if we could do. So in Australia, what we did was we decided that we were going to put quite a bit of effort into calibration. And why would anybody go to Australia for calibration work? Well, mainly because we are in the southern hemisphere, and you know what? When you're in the southern hemisphere, and if the sensor is launched in the northern hemisphere winter, we have an advantage because we are in summer, we've got good conditions, etc. Importantly, we have actually very, very clean air. 70% of our areas are arid, dry, there's no land rainfall, there's no vegetation, there's no probability of cloud, and we have very, very clear skies. And I don't think this is correct, but when I first went to Australia, they say to me, you know, in this place we have 361 days of sunshine. So, and literally, if you go to Perth, a lot of times you look up and it's just blue. It's just completely blue, right, Pilon? And you know, we have a huge landmass that's as big as America, as the USA. But we have very, very low population compared to our landmass. So we have quite a lot of area which is away from population. And if you remember the criteria from what Kirk was talking about, have to be away from the influence of urbanization. We have a very flat country, and this is also one of the jokes that they have in Australia. Our mountain is a hill compared to most countries, so we're really flat. And importantly, you know, Australia is one of the biggest users of Earth observation data. We use Earth observation data for 92 very, very important missions or projects for government services. But yet we don't have any of our satellites. We actually use other people's satellites, right? So for me, the work that we do here is a way that we can give back to the space community as well. This is what we can actually contribute to them. And what can we do differently? Okay, so for me as well is that I'm an imaging spectroscopy nut, as everybody would know. So the thing that I saw the gap is that we don't have a site specifically built for imaging spectroscopy, and this is where we can actually make a little bit of difference. And then we really want to make a site that actually is of international standards, and this is where I defer to Kirk actually, because he's the CSWGC chair, and hopefully we can make a site that's endorsed by the CSWGC, and hopefully even better than that. So just a little bit of background why people in Australia are very interested in imaging spectroscopy. In terms of the eye people, the geologists, well, imaging spectroscopy and spectral calibration is very, very important for us because we need to map minerals, and subtle changes in mineralogy or subtle changes in the absorption features of mineral features actually can help us understand where the best place to mine or to the best deposit is. And this is an illustration of kaolin disorder, and it can actually tell me where the depositional material is and where the erosional material is. So you can see up there, the changes are actually really, really small. It goes from 1.9 microns to 2.2 microns, the absorption feature. So, you know, it's really important that we are able to track those kind of features. So this explains why it's important for us to understand these kind of minerals because it then tells us which part of the landscape we're in, because people are interested in the fresh rock. So basically, primary minerals replace the iron oxides. So I didn't actually expect this to click on, but this is where we have actually mapped the poorly ordered to the well-ordered crystals, kaolinites. And so this then tells the miners where they can actually mine. So this is important. And that example was in the shortwave infrared. Why the shortwave infrared is really, really important for us. Then there's the visible near infrared. We shouldn't forget that. That's also very, very important for us in a mining country, because it can tell us about iron oxides. So features, although are really broad for minerals in the iron oxides, the variation in where the absorption features are tells us whether it's a hematitic iron oxide or graphitic iron oxide, as you can see there. And that is actually important for the quality of the ore. How much can we sell it to China for example? So where it is in the profile then tells us where we can get these minerals. Anyway, so back to site characterization. So when I embarked on this work, I scrounged the literature to find out what are the things that I need to take care of to tell me what is the best, what are the indicators? What is, as Kirk tells me, what is the tick list? What is the type of characteristics that I need for a site? So I found this paper, and basically there are a list of I think in order of importance, it seems, yeah?
No.
No, Kirk doesn't agree with me, and probably I'll agree with him. I'll tell you later that as you actually go through the work, then you know that really these are a set of guidelines. There's no right answer, there's no wrong answer. You just need to know what your characteristics are, and when you actually find the characteristics or there's something that doesn't match, then you need to balance the different characteristics, and say, okay, what can I give away? And if I give that away, what kind of equipment do I need to, or what kind of measurements do I need to make sure I understand it? I think that's the story. But anyway, there was a list of physical characteristics, right, which Kirk has gone over quite a bit. Then there's a list of environmental conditions. Clear skies, long distance away from facilities, and I explained to you that Australia has lots of places that has all the kind of characteristics. And arid zone, of course, 70% arid. The thing is that one of the things is location. How you actually can get to the place, and I think Kirk was saying driving 7 hours, driving 14 hours, those kind of things has to be taken into consideration. And in fact, actually, after doing the work, we would also add communication. Can you actually communicate with people? And I guess there's the instrumentation. So when I embarked on the work, we already had a vicarious calibration site that we selected. And it was actually mostly good in the visible infrared. And I won't say what this is. But I thought, okay, how can, we have a large area. How do I know where to actually go to pick the best site? Do I go by intuition? Do I go by, do I just go to my backyard because it's nearer? Or do I go into the middle of the desert because I know that there's sand dunes there, and it's easy for me to find areas that are large and and flat, maybe. But then we thought about it and go, okay, at the time, Australia had the AGDC, the Australian, what was it now? But basically it's a collection or an archive of all Landsat TM data from the time the Landsat TM was launched, from 1970 to the time I did the work. We had this huge archive of all the data sets that were collected for Australia. Remember that we are actually trying to calibrate. Why is it going by itself? Remember that we are actually trying to calibrate for sensors that are 30 meters. Landsat TM is 30 meters. We have this huge archive. How do I understand what is the most stable landform that's actually not going to change over time, going to be spatially homogeneous, etc. over time? Use the Landsat TM archive maybe. So that's what we did. So what we did was we used the Landsat TM archive, but we didn't use the complete one because it was easier if we actually used, one series of Landsat TM. So it covered the right spectral range, although it's not hyperspectral, because all we can get our hands on, and we have to revert back to what we have, is discrete bands, multispectral. But it does cover the visible to shortwave infrared. Has the 16-day revisit time, so I can actually look through the different seasonal cycles and make sure that everything's fine. So then what we actually have to do, then we have to actually put criteria on our site selection, right? We have to make sure that the areas that we're looking for is actually spatially homogeneous across at least 3 by 3 and preferably larger pixels. It has to be a high reflectance target. And Kurt would say now that would disown this, but I did find a paper from Kurt that actually said that it would be preferable if your reflectance is larger than 30%. In fact, he actually gives me a hard time for saying that, but it actually saved my life. It saved my sanity in a way, because if I actually set a target for 20%, there will be heaps more areas to look for, and I would go crazy.
Well, I'll agree with the 30%. I know I said that.
Yeah.
Yesterday you were saying 40%. And
No. I set it higher to 40%, and I'll explain why later, why I actually set it higher to 40%. And hopefully we have a spatial and temporal homogeneity, consistently no vegetation, and it's flat, low relief, and it has good climatic conditions. So, huge data set, can't do this all on our own. We had all the archive already put in the supercomputing facility, and I didn't do this work. My colleague, Michael Chatter, actually did this for me. I set all the criteria for what we wanted the end result to look like. So for example, we set an NDVI of larger than 0.3 because I knew that most of our vegetation would be larger than or smaller than 0.3, so we get all the background. And we set criteria and indices for surface water, so we can remove all the effects of surface water. We set criteria for cloud. We set criteria for the number of observation, so that we wouldn't actually be getting statistics just for one date, which would bias then our choices. And then we calculated 3 things. Actually more than 3 things, but we calculated the albedo across the full wavelength, because remember we are actually trying to look across the whole wavelength, average from the visible to shortwave infrared. Then we actually calculated the albedo for the vernier only, and the sewer. And I will explain later why we did that. So we calculated then the statistics or the mean across the 10 or 8 years that we actually did the work on the complete archive. The mean and standard deviation across that. Why does this go by itself? Anyway, so this is more or less the summary of the results. So we got the Vernier albedo. We got the coefficient of variation, which tells us the variability across the years. The coefficient of variation is the mean divided by the standard deviation. It tells us the variation across the years. And the normalized occurrence, how many times did we actually get acquisition across the area. So red means there's more times. Why does this go by itself? Sorry. So then we set criteria for how we actually then get to the areas, our final search, our final areas where there's background. This is the best area that we can actually go to. So we set criteria for the total number of observation, 40. That is, it actually have low NPVI areas that has no green vegetation. Remember, we can't actually find where the dry vegetation is because we can't actually measure dry vegetation with the Landsat-TM imager. We actually initially set a criteria for the full visible and shortwave infrared on 30%. But then we actually then revert back to setting the criteria 0.3 for the Vernier and 0.4 for the shortwave infrared because we found that a lot of our dry vegetation was coming up higher than 0.3. So if I don't know whether you guys know, dry vegetation have features in the shortwave infrared, right? And clay minerals, many different minerals have lots of features in the shortwave infrared. There's a lot of confusion in that area. So and what we found is that when things are bright in the shortwave infrared, actually a lot of times is dry vegetation, but there's a mixture with other minerals as well with background. And then we set a coefficient of variation to make sure that it doesn't change too much between dates. So as a first cut then, we found, so what we did was then, this was the result, and I don't know whether this come out properly, but what we found was that, of course, in the middle of the desert, what we call our central desert, comes out as the bullseye. This is the big place. This is your search plane. But there are other areas that comes up, our salt lakes. Especially in the visible shortwave infrared statistics, we found out that all our salt lakes pop up. Many salt lakes. But we already have a salt lake as a invariant target, remember that? Or vicarious calibration target. All our beaches comes up, all around the edges. But then you have to think about the criteria that Karen Scott and Kirk put together. Your climatic condition must be good. So around the coast, a lot of times, your rainfall zone are actually quite high. So the green, I don't know whether you can see properly, but I'll give you guys this slide to do your practical afterwards. A lot of our coastal areas are actually in the high rainfall zone area. You also have to think access, how do I get there? So the red rings you see is the closest area of 400 kilometers to the site, or your closest airport, to the site. So, I already said that. So basically the results show that many of our salt lakes actually come out as very good targets with high spatial homogeneity, and really spatially homogeneous. but temporarily, as in, between days, it changes quite a little bit, and it only works in the visible infrared. And Kirk actually showed white sands, and it's very similar to white sands. White sands is a gypsum area. We have halite. Most of our salt, I think, it's halite salt lakes, and actually meets the albedo threshold for the visible infrared, but is very low in the shortwave infrared. Coastal sands, they are spatially homogeneous, but of course they are not as good as salt lakes. So between days, they're actually quite coherent. They actually don't change too much between days. Because they're actually a sand dune or coastal sands, can meet the threshold criteria across the full visible to shortwave infrared range. But remember, one of the criteria is not too near the ocean, because we might actually hit the problem of the aerosols, right? And also a lot of these areas are sand dunes. So topography, remember shadowing and different things. And then the other areas are the inland sand dunes. As I said, the central desert came out as the biggest place we should search for. That's the bullseye. Spatially, they're as good as the coastal sands. Temporally, they're as good as the coastal sands. Meets all the threshold criteria for visible to shortwave infrared. But the thing is, it's true outback. You have to actually drive a long way to get there, a really long way to get there. So these are the things that we come up with. So I'm going to, I guess the thing is that we have to then have to consider, okay, we have all these things to think about, because even though we try and round down our searches so that we can actually go to the best place, we still have so many choices, we already have a salt lake, but the thing is, the salt lake doesn't meet the complete criteria. Where else do we go? How do we actually choose? And I guess this is then my exercise for you guys. And I probably didn't go as long as I should have. Correct?
No, you can go short. Nobody
Okay.
complains.
So
You had an hour and a half if you wanted it. So.
Okay. I actually don't have so much. So I guess the thing that I'm trying to show you is the 4 sites that we are actually we had the choice of making, right? We have four sites that we think, okay, that might be where we are going to, okay? And I already described to you that we have a salt lake. And maybe I actually gave away 1 point to you guys, because I told you that the visible infrared is really good for the visible infrared sensor in the salt lakes, and not so good in the shortwave infrared. So maybe I already gave you the answer for one of the sites. But the exercise that I'd like you guys to do, I don't know whether you guys, I guess we'll do this before lunch then, correct, won't we?
We can start if we get done before lunch. That's great.
Okay, we'll do it before lunch then. So I'll describe to you the 4 sites, right, that I have set for you guys to have a look at. And I want you guys to think about the different criteria that you need, the selection criteria that you need for a site. And I want you to, and I will tell you now, there's no right or wrong answer. but I want you guys to tell me I want you guys to choose a site and give me the rationale why you chose this site. Okay, does that make sense? Okay, so I've already given one answer away, but doesn't matter. One of the sites is actually a salt lake. It's called Lake Lefroy. Okay, it's actually quite an easily accessible area. You fly into an area called the capital city you'd actually land in if you're international person is Perth in Western Australia. You fly into Kalgoorlie, and from Kalgoorlie you actually drive only 60 kilometers to this small town called Kambalda, and it's a mining town, and you have this huge salt lake that's 50 kilometers by 10 kilometers. Flat, really nice, bright area. It's got vegetation around it, and it's got this really thick salt crust of 10 centimeters at least, not at least, in the thickest area, but at least 1 to 2 centimeters in the thinnest area. You can literally walk on it. And before I start assigning you guys to different groups, I'll tell you now that the people who already are familiar with the areas will actually help me go around the groups and talk to you guys about the site. And Yama-san and Obata-san have been working with us and Chris quite a lot on this site, so I think it's quite unfair for them to actually participate in this because they already kind of are biased. So they're going to help you guys with the site selection. So the climate in Lake Lefroy is perfect. It's in an arid zone. It's got very low rainfall, and there are areas where the big parts of the year where it's sunny all the time. And think about the security of the area. This lake has public access. It's actually used for recreational area. So people actually land sail. Do you know what land sailing is? Do everybody know what?
The world record was set at Ivanpah Playa.
Sorry?
The world record for land sail speed was set at Ivanpah Playa.
So we have the equivalent. So basically you have a catamaran type thing. You go on this lake and you just zoom along, and I don't know why you would do it, but people do it. But there are other areas within the lake that have secured compound. Think about communication. We have satellite communication there. We have restricted areas of 3G. And think about that if you actually put a site, instrumentation on the site, right? What are the roadblocks to actually you putting it on the site? You have to ask for permission, right? How long does it take for you to actually ask for permission from different organizations and different things? You have to think about that. So this is the climate data. So you guys, I'll give you all this kind of information so that you can actually go through it and say, okay, how do I actually decipher this and actually make sure that how do I justify that I chose this site? So I'll give you the statistics for the area as well, so that I've calculated. So this is the visible, the infrared, shortwave infrared means. This is the temporal changes across the year. This is the shortwave infrared means. And this is the changes in the visible and infrared across the years. And this is the changes across the whole visible to shortwave infrared. The second site that we have set for you is the Pinnacles Desert. This is a site that is very close to Perth. It's 250 kilometers north of Perth. The nearest small town is 20 kilometers away. It's sealed roads all the way up to the national park where it is located. The park is actually really famous for the pinnacles. And we actually have to walk into the sand dunes, which is 1 kilometer away. The landform is, of course, as I said, sand dunes, but it's not high sand dunes. It's actually undulating sand dunes. But the size is actually not big. It's only 2 by 5 kilometers. And I'll tell you what the materials are. And there's the vegetation. There's lots of small little coastal vegetation surrounding it. And wildlife, of course, because it's a national park roaming around the site. Communication, because it's so near to Perth, you can get most forms of communication. The permission, remember I said, what are the roadblocks to actually putting instruments in there? It's actually in a national park, so you have to get national park permission. Because in Australia we have Aboriginal heritage area, permission from the Aboriginal heritage. Need to minimize disturbance because it's a national park. But there are areas, and you will see, where people have already built something there. Because it's a national park, people have already erected some buildings there, right? And security. The park. And parks are looked after by rangers, by people who roam the area a lot. And the area that we're going to is not where the tourists are going to. It's 1 kilometer walk away. And we have been there 7 times now, and we have not seen any other footprints besides our own and the emus and kangaroos, which is actually really cool. The metadata, these are the aster data. Remember I was saying that the composition of the ground is also important. So I'm actually going to give you, for the other sites outside of the lake, which is actually just mainly halite, the composition, the different materials that are actually on the site. So this you will see the carbonate abundances, the silica or the sand abundances for the area, the clay abundances, and also similarly all the different statistics that we calculated. Did you have a question?
Yes.
Okay, so all the different statistics and also the DEMs, so you can judge whether, which area should I actually put this site. Okay, the next site that you will work with is Esperance, right on the coast, on the southern coast of Western Australia. It is 727 kilometers south of Perth. But there is a small airport in Esperance. And the site that we've chosen is 14 kilometers away from the town. The roads are sealed all the way up until you get to the beach. Then it's four-wheel driving all the way into the dunes. These are pretty big sand dunes. But you see, it's beautiful. It's like snow. Coastal vegetation again, communication is not so reliable. So most likely we will be relying on satellite communication. Also national park and also Aboriginal heritage. But remember, this is an area which is very, very beautiful sand dunes. In Australia, people like to go four-wheel driving in sand dunes. This is a recreational activity in the weekends. So you will see that it's very popular. That area is very popular. So the composition, I will give you all the composition maps again of the site, of the area, which tells you what the material is, how even the distribution of the material is, and I will also give you all the statistics for it. Additionally, to all the things that I'll give you on the slide here, I'll give you all the slides here. I will give you spectral data, and I have actually ViewSpec Pro on the disk as well, so you can load the ViewSpec Pro so you can view the spectra. I will also give you photos of the site so you can get an idea of what the site looks like to make a better judgment. Okay, I think this is the last slide, the last site that we're going to decide on. Remember I said Central Desert was the bullseye, was the area that was the key area that we were going to look at. However, if you think about it, this is the Central Desert. It is about 700 kilometers away from the nearest big town, Adelaide, in South Australia. Sealed roads all the way to Lyndhurst is about 600 kilometers. Good sealed roads to Murray, which is another 80 kilometers up. And we have actually chosen a site that is flat sand plain. This is unsealed roads for a good 100 kilometers away. All in all, for you to get there from Adelaide, it will take you 1 day to get to Murray. For you to get to your site, it's going to take you at least 2 hours from Murray. Okay, so I did tell you about the access. You can actually go to a nearer place for the airport. It's called Olympic Dam. Olympic Dam is, Pyongyang would know this, is actually one of the biggest uranium mine in Australia. But it is a mining site. To get any equipment, any materials is going to be difficult. So think about that. The nearest town and accommodation is Murray. Theoretically, there's actually a place you can stay on the Morolina station, 50 kilometers away, but you can't because the BHP Billiton mining company, which owns Olympic Dams, actually booked up all the accommodation for all the people. So you have to stay in Murray, which is 100 kilometers away, and it takes you 2 hours to get to your site. So, because of that, the best place for you to land would be in Adelaide. And you have to bring most of your supplies because Murray is a very, very small town, and even drinking water can be difficult to get. So you have to bring your own drinking water. And Chris can explain this because he went with me. But this is a huge area. This is, if it worked out, it would be actually a really nice site. So the lake area, the whole area is 144 kilometers by 77 kilometers. It is the lowest point in Australia. The lake itself, though, gets flooded every 8 years. But it only got filled to capacity 3 times in the last 160 years. So potentially the lake could be used too, maybe. The surrounding areas of the lake is covered by red sand dunes, mesas, and salty clay plants. And this thing called they call the Gibber tabulans. It's like a bit of a mesa thing. The vegetation is very sparse. There's lots of mango grass, lots of acacias. So, like, I think what you see here is very dry grass in small clumps, but spread across the area. And the other thing is, this is an area where they raise cattle. So you find a lot of animals actually eating I actually felt quite sorry for the animals. The cattle are actually eating this dry grass material. Communications. This is a biggie. In Mari, theoretically you got broadband coverage, but you get there and it's zero. No coverage at all. Okay? You must have satellite communication. There are areas which we looked at in terms of permission that is in BHP or the mining list area now. So there are areas where you actually have to get permission from the mining company to access. And it's actually locked up. The gate is locked up, so you cannot pass without it. Because it's actually a very big national park, it is actually required for you to get national park permission as well, and it's also an area where you need Aboriginal heritage permissions. But in terms of climate, this is a perfect area. The aerosol optical depth always in the 0.0 something, it's very low aerosol, very clean, very dry, very hot, but low humidity. So it's, in terms of climate, it's actually a perfect site. I'll go through that. I'll give you for the big search area that we had, the different statistics that we calculated from Landsat TM, as well as the DEM, so you can go, okay, which area would I go to? I know this doesn't come up too well, but the area that we actually went to was the sand plains, and I will show you the, I guess the decomposition material as well. So you have all that. So what I will provide you now is a USB stick with all the information about the photos, the spectra, and finally the Hyperion data. And so if anybody, for most of the sites, so if anybody is enthusiastic enough, they can actually try and have a look at the, sorry I didn't actually say that yesterday, they can actually have a look at the Hyperion data as well to make the best judgment.